Hi, I'm Daniel, and welcome to Willing Suspension of Disbelief. I want to start by taking you back almost 30 years ago to a show named Mantis. IMDb describes the show as a paralyzed African-American scientist builds a powerful exoskeleton in order to walk again and uses his new abilities to fight crime. Although it wasn't on the air very long, this was one of my wife's favorite shows. She watched it every week until this one episode that featured this villain who could travel through the electric grid. He could go into one power socket and travel through the grid and come out another socket. I didn't understand her objection. I mean, if you think about it, she was fine with that paralyzed African-American scientist building a powerful exoskeleton to fight crime. That was okay. She drew the line when the villain could travel through the electric grid. That was too much for her. As crazy as the premise of the show was, she accepted it. That's a willing suspension of disbelief. For her, it was a well-conceived premise. So that's how she came to watch and stop watching Mantis. So what does this have to do with async await? We've seen discussions around avoiding threads and making all this simpler before. In 2008, as part of the Snow Leopard release, Apple provided a new technology and they included this technical brief for it. The dominant model for concurrent programming, threads and locks, is too difficult to be worth the effort for most applications. They went on to say the problem is far more complex than simply breaking tasks into threads. And they offered this solution, Grand Central Dispatch. Apple marketing told us that Grand Central Dispatch is a revolutionary, pervasive approach to multi-core processing. GCD shifts the responsibility for managing threads and their execution from applications to the operating system. As a result, Apple told us, programmers can write less code to deal with concurrent operations in their applications, and the system can perform more efficiently. So in 2008, that was their solution, Grand Central Dispatch. In 2021, they told us, nope, that's not the solution. In fact, there are problems with Grand Central Dispatch. We have a better solution for you now. Async await and friends. Because we bought the earlier premise, we had to have a willing suspension of disbelief to go with them again. But async await is very different than GCD. In this talk, I want to cover some of the ideas behind async await in Swift. So let's begin with an evening out at Cafe Async. We find somewhere safe to go with a friend, and when the waiter approaches us, we turn and say, "Please bring some water for my friend." Now, this is, of course, a server request, and we all know that server requests can take a while. Here's option one. After we ask the waiter to bring water for a friend, we just wait. So here's the server ordering water, and we wait, and we wait. And while we're waiting, it would be nice if we could do other things, but it turns out we can't. I can't even go on to the next line, which doesn't depend on me getting the order at all, where I just turn and ask my friend, "What are you drinking?" Finally, the server order is fulfilled. The server has brought us back water. We assign it to my friend's beverage. And now I can ask, "What are you drinking?" And now my friend can respond, "They brought me water." My friend.beverage has been updated and it is water. So that was option one, where we just wait. But of course, something can go wrong. The waiter could have gone back to the kitchen looking for water and maybe they were out. Maybe they didn't have any of the special kind of water that they sell at this establishment. And so we need to deal with the possibility that calling order might throw an error. If the order method can throw, we need to call it with some sort of try. And if we're not going to rethrow the error or propagate it some other way, we need to wrap that try inside of a do, and we need to handle the try inside of a catch. And so the order throws, and we use a do try catch in response. So this isn't new. We use throws when we declare order so that we know it can throw an error. And when we call something that throws, we use try to acknowledge that it can throw an error. This pairing, this throws and try together with a do and catch, make it clear that order can throw an error and that we are acknowledging it and that we are handling it. And so one of the big ideas behind async await is that we should probably have similar words and patterns that make it clear that maybe order takes a while. Maybe we're going to be waiting. We'll get to that soon, but first we're going to look at another aspect of why we'd like to sort of clean up our code using something like async await. And so let's look at one of the practices of how we currently deal with something that runs asynchronously on another thread while we're going about our business doing something else, and that is closures. So we're back in Cafe Async, and I asked to please bring water for my friend, and the server goes on to fulfill our request, and I sit there quietly with my friend, and then the server returns, but my beverage is wrapped up inside of something. It is inside of this closure. And we look at it and we say, well, how do we get our drink out of there? So let's see what that might look like in code. We're going to ask our server for some water in a different way. And there's this space between where we order and when we get our friend's beverage. Sometime between when we order it and when my friend responds saying, I got water, that water has to have been set. So let's see how it's done with closures. In fact, I'm going to use a singleton. We're going to use a shared server. A server is shared among many tables, perhaps. And we order water and we wait for the results and we respond to those results in a callback, in this closure. And when the closure gets called, the beverage optional and the error optional will be populated. Oh, and of course, a server request won't be initiated until you ask it, please. Okay, let's get back to the inside of the closure. This is what gets called when either we get our beverage or we get an error. If there's an error, we unwrap the optional and we somehow handle that error. Otherwise, there was no error, so we check to see, do we have a beverage? Now, there is a possibility, it should never happen, but it's possible, that there was no error set and there was no beverage set, that they're both nil. We should probably deal with that with a fatal error, but somehow we're going to handle no error and no beverage. Let's not worry about that. If we are able to determine the beverage, then we want to somehow assign the beverage to the right person so that my friend can respond appropriately later. But I'm stuck inside this closure. And I've got all this gunk here. In fact, if we look at this, and this is kind of small because I've just used comments instead of the actual code, there's a lot of code here. And the order of the code is kind of baffling. Some of the code follows code where we're checking, is there an error? We're inside of a closure. It gets called maybe later. It's very baffling. The closure is executed on a background thread. We need to get back to the main thread in order to do anything in the GUI. And so as the code stands right now, my friend is responding before they've been served the water. As goofy as that is, I'm more concerned with the inflexibility. You can see that my friend is hard-coded into the closure. That's probably not a good idea. So let's wrap our call to the server inside of another function. Let's create a function called order, where we specify the beverage and we pass in some completion. And so when we call this order, we can say who we're ordering for. We can have that specified in our completion. And so now when you look at what order does inside of that closure, we call that completion that's passed in. So we get our flexibility that way. So we know what to do if there's an error. We can specify what to do if there's no beverage and no error. And we can specify what we want to have happen if there's no error and there is an actual beverage. Still a lot of code, still a lot of ugly code, but we can use it nicely. The way we use it is we make our order request. We say we want water, and we specify what our completion is. Our completion takes a beverage and an error, and we can say inside of it, we'll just deal with the case where there is a beverage and no error. If there is a beverage, then set my friend's beverage to be bev. From the perspective of the caller, a little better, a little more flexible, still a lot of code. But we didn't have to hard code my friend inside of our function. We're passing my friend in. So that's a quick look at closures. This year, Apple gave us a new solution and went back and supplemented a lot of their existing APIs with async versions. In this case, when we ask to please bring water for my friend, the server lets us know right away it's going to be a while. And they tell us to go on and carry on. Now, we can't do anything that is in that same flow of execution, but Life hasn't come to a standstill while we wait for this server. So we chat amongst ourselves about other things, and at some point the server returns and says, here's your water. And we go back to our original thread of execution, and I ask my friend, what are you drinking? And my friend responds, it's water. So for inspiration for waiting, let's look back at errors. When it was possible that order threw an error, we had to annotate what came back from order with throws. It throws or returned a beverage. This wasn't the closure case. This was a case where we were waiting and could throw an error. And we handled the error inside of the do, try, catch. So let's forget about errors for now, and let's just deal with the fact that maybe order takes a while. Just like with errors where throws makes waiting explicit and try makes the fact that we're calling something that could throw explicit, we're going to make waiting explicit. The async keyword tells us that order could be a while. That's where the server turned to us and said, hey, it's going to be a while. Now, when we had something that throws, we used try, and with try, we did one of two things. Either we handled the try in a do, try, catch, or we placed it in a function that also throws. So here I am calling server order. Because I'm calling server order and order is async, I have to use await. And if I use await, just like with try, I have two choices. Either we can create a task to pass it to, just like we had our try inside of a do block, or we can place it inside of a function that is itself async. Now, we've already seen what that second one looks like. Here's order, it's async. To declare a function async, that's how you do it. So instead, I'm going to show you how to create a task to pass it to. So order is a method that is async, and I want to call my beverage, which uses await. In order to use await, either I could wrap this call to server.order inside of some method that I declare to be async, but we said we want to look at the other option, which is to wrap this inside of a task. A task will start what's inside executing on a background thread. Now, we can have both errors and async. So here's order that is async, and here we use it using await. If order could also throw an error, then we use async then throws in the declaration of order. And when we call it, we have to try then await. And so async throws pairs with try await. Combining both adds a little complexity to what we're talking about now. So I want to leave the throws and try for another day and just focus on the async await. So I've taken my call to server.order, which I need to await on, and I've wrapped it inside of a task. Well, since await is inside of task, what happens with that me.ask? Currently, it's like our closure example. We continue right away to me.ask. And then we continue on to my friend's beverage, but my friend's beverage hasn't been refreshed yet. It's still whatever it used to be. The water hasn't been set yet because that's happening on a background thread. That may not have completed because that's a long-running task. And so I've gone straight from task to me.ask to my friend responds too quickly. So one option is to move everything inside of task. But now we're back to the old days when me.ask is waiting for the server order. Now everything after task can continue, but everything inside is waiting for that first await to complete. I think it's helpful to take a step back and take a look at the order of what's going on inside of task. So the first thing that happens is we place the server order. Now that's something we have to await. So everything else pauses. Nothing else happens until we hear back from that server.order. We can think of this as a suspension point, and you think that's no better than the old days. Well, the good news is, since nothing else inside of this task can happen until server.order is fulfilled, we can free up this thread for the system to use it for other tasks. So the system can address its resources for other things until server.order resumes, and now our task picks back up, possibly on a different thread. At some point, our server.order returns. We can go ahead and assign that result to my friend's beverage, and then we can carry on. I can ask, what are you drinking? And my friend can respond, it's water. Now, this seems a little bit messy, because it would be kind of nice if while I'm waiting for the server's order to come back, I could execute any line that doesn't depend on that server's order. In other words, why can't I ask, what are you drinking? My friend can't respond yet because my friend's beverage hasn't been set, but I could ask. And that brings us to async let. Here, when I ask for water for my friend, the server says, yes, it's going to be a while. That's the await bit. Tells us to carry on. The only thing we can't discuss is whatever depends on the response to that server request. So we chat amongst ourselves. Then finally the server says, here's your water. And now I can ask, what are you drinking? And my friend can respond, water. In this code, I'm just going to use a local variable for my beverage. What we did before was we suspended when we made our server order, and nothing else could happen until that server returned with the results of my order. We're going to take that await and we're going to move it with syntactic sugar to the other side. It's sort of an affordance that tells us we have to suspend here. We're going to move it to the left side to say, really, nothing should move until beverage is set, but everything else can keep moving. And we do that with something called async let. So async let is an affordance that says the thing that we're waiting for, the server.order, is going to take a while, but I don't want you to move on with anything that depends on beverage until beverage is set, but you can move on with everything else. So the only thing that depends on beverage is my friend's response. And since my friend is waiting for beverage to be set, we have to indicate that with an await. It's as if the assignment let beverage equals has been marked async. So when we call something that depends on that beverage, we have to use await. Once again, let's trace the action. Server.order is something we have to wait on. We have async marked on the left side, so we're suspending until that server.order is fulfilled. I'm free to go on and ask, what are you drinking? But my friend can't respond, it's beverage, until beverage has been set. So when the server returns with our water and the beverage is set, now I'm no longer awaiting my beverage. It's been fulfilled, and so I can use it inside of my friend responds, it's water. And that's async let. Next, let's consider actors. We think of the server as our waiter, there to respond to our requests. But actually, the server is serving many tables, and each table is making their own requests. This can be confusing to a server. It can lead to deadlocks. It can lead to inconsistencies. It can lead to job dissatisfaction. And so the server announces, I will only listen to one table at a time. This enables us to think of our server as our waiter and not worry about other people's requests. Sometimes we might need to wait while they're taking care of another table, but when they're with us, we think of them as our waiter. Fortunately, many waiters are aspiring actors, and we'll see why that matters. So let's begin with the class. With the class, a waiter isn't able to just listen to one table at a time. And so when I ask, please bring water for my friend, and someone at the next table says, please bring water to my friend, there's nothing to synchronize those requests. And what if there's only one bottle of water in the refrigerator in the kitchen? So server is a class, and server has a private refrigerator. We can't see it from the tables, but when the server goes into the kitchen, they can see the refrigerator. And when we place an order for a beverage, the server says, well, it's going to take a while, and we could get an error out of this, but I'll return with a glass of something if I can. For now, let's not worry about the asynchronous. Let's just worry about the throws aspect. So when we order a beverage, it either throws an error or it returns a glass containing that beverage. The first thing that happens is the server checks to make sure that the refrigerator contains that beverage. If it doesn't, order will throw a beverage not available error. If the refrigerator does contain the beverage, then we'll remove that beverage from the refrigerator and prepare it for the customer and return it in a glass containing that beverage. Here's the issue. Between the moment that we check to make sure that the refrigerator contains the beverage and when we remove that beverage from the refrigerator, some amount of time has passed. And the problem occurs if two tables ask for the water at the same time, because it could be that check has been made for both of them, saying, yes, the refrigerator contains the beverage, and whoever gets to the refrigerator first to remove the beverage, they get the one remaining bottle, and the other person doesn't, but we're no longer using our guard clause, so it's undefined what's going to happen. We're probably going to crash. So here's how we get two tables to make the same request at the same moment. We wrap each request inside of its own task, and now the two tables have asked for the water at the same time, and if the order is placed at the exact same time, the guard clause may be true for both, but there's only that one bottle of water. Now look what happens if we change our class to be an actor. An actor is a reference type, just like a class, but there are rules for when you access and mutate the state. An actor is designed to make shared mutable state safe. So when we're not able to use a struct or a num or something that's a value type, when we have to use something that's a reference type, an actor is a way of making sure it is safely accessed. I still have two tasks making that same server's order at the same exact time, and because I don't know who wins, I need to mark this with an await, because maybe beverage 1 is going to have to wait until beverage 2 is fulfilled, or maybe beverage 2 is going to have to wait until beverage 1 is fulfilled, but I don't have to worry about them both being inside asking, is there this drink in the refrigerator, and then being in some inconsistent state. So that's a quick look at actors. I want to look at one last aspect of async before we wrap up, and that is async sequences, or their concrete representation using streams. To make this simple, I'll go to Cafe Async by myself, and I'll ask the server to bring me whatever they want. And in fact, just keep them coming. Bring me out whatever drink you want, however often you want to. Maybe somewhere between 5 and 10 drinks. All right? So as not to confuse these examples, my server is back to being a class, and this class contains a stream of drinks. It is an async stream that is going to be filled with beverages. Beverages like water, coffee, beer, wine, different beverages. And when I create an async stream, inside of this closure, inside of this last argument, I say, here it is an async stream that is going to handle beverage instances, and I am passed a continuation. And this continuation is what's going to enable me to return values as they occur. So because I'm going to do some asynchronous coding, I'll put it inside of a task, and we'll pick a random number of drinks that we're going to serve this evening, somewhere between 5 and 10. And as long as I still have drinks to serve, I'll serve them. But when I'm finished, somehow I need to say I'm done, and we do that by saying continuation.finish. When we call the finish on the continuation, we're saying there's nothing more coming from this async stream. And so if you're using some for-in to enumerate through the elements of this stream as they come up, when you get continuation finished, you know, we're done. There's no more coming. If there are more drinks to serve, then the first thing we'll do is decrement the number of drinks left to serve. We're supposed to leave some space in between, something to allow the customer to drink a little bit of their drink before we bring the next one. So we'll pause for some amount of time to make this asynchronous. And then we want to return a random drink. So we'll call beverage.randomDrink, and the way we get it out of this closure is we use continuation.yield. So the continuation is the way that we get information outside of our closure. It's kind of like what we did earlier when we dealt with the closure explicitly when we wrapped our call to the server inside of another function where we defined the completion. Here it's the continuation and it's been defined for us. And the result will be that we return a stream of drinks over time, somewhere between 5 and 10 drinks. Okay, I'm sitting at my table ready to receive my beverages. And so here's my function, receive beverage, and I want to iterate through all of the drinks that I get returned from this stream of drinks. So I use that for loop that you know and love. So inside of receive beverage, I'm going to iterate through this stream of drinks. And for every bev in the server's stream of drinks, I'll display it on the screen. I'll let self.drink equal bev.description, and that will appear in some text on the screen. And when I'm done with all the drinks, I'll display that's all for this evening. But how do I iterate through this stream of drinks? It's a stream. I don't know if it ever ends. I don't know when it ends. Stream of drinks is an async sequence, not a sequence. So the way I iterate it has to be different. I can't just loop through every bev in server stream of drinks because every bev isn't yet in server stream of drinks. And so again, we use the keyword await. For await in says, as each new element in this stream appears, go ahead and assign it to Bev and then execute whatever inside of this for loop. And because I have an await inside of this method, either I have to put this for loop inside of a task, or I have to mark receive beverage as being an async method itself. And so let's do that. Await bev is another suspension. And so what's inside of the for loop waits. And each time there's a new bev, then I can go ahead and execute it. And that's a quick look at async sequences. So we've seen a lot. Async and friends is not Grand Central Dispatch. In GCD, we work with queues, not threads. There are still threads. In fact, there are lots of threads. Syntactically, async await feels more like throws and try. Remember, throws and try, if a method can throw an error, it has to be marked throws, and if we call a method that can throw, then we must use try. When we use throws try, there aren't more or fewer errors. It doesn't change the number of errors involved. It just makes it explicitly the way we're calling them out, and it makes them handy to deal with. That's throws try. With async await, if a method can take a while, and I don't know exactly what I mean by take a while, but it should be marked async. And if we call an async method, we have to use await. Async await forces us to be explicit about this asynchronous code. It also allows us to write more linear code with these asides. Async await is not a parallelized superhero in a bug suit. When you see async await, think suspension. So as we saw, this is a suspension point. We're awaiting the server's order. Everything else is waiting for it. So we free up the thread to do other work while we wait. When it's fulfilled, now we can go on with the contents of this method. We can go ahead and assign the result and go on and ask, what are you drinking, and so on. So this is a suspension point. With async let, this is also a suspension point. We have to wait till server order returns to do anything with beverage. But in the meantime, we can continue to do things that don't depend on beverage. Once order returns, then beverage exists and we can go ahead and use it. In the case that server is an actor, these are also suspension points. We don't know which request to server order is going to get through first, so we have to assume that we might have to wait. And we're protecting ourselves against that by saying, here's a point at which I might have to wait. And finally, when we had a stream of drinks for async sequence, we marked bev with await because we didn't know when we're going to get the next element of the stream of drinks that we could use inside of our for loop. So this is a suspension point. These are our willing suspensions. Thank you for joining us this evening at Cafe Async. Please remember to tip your await staff.